Hello, we are going to present the main aspects of the experiment that we conducted within the Green Lab course. The topic of our research is energy consumption across collaborative software applications. In the modern, rapidly changing world, collaborative software applications have become essential tools. They play a crucial role in enhancing communication and teamwork and have evolved to become vital platforms for a wide range of activities, such as online interviews and remote collaborations. So, in this interconnected world where reliance on collaborative software application is extensive, understanding their energy consumption and the resulting environmental impact is important. This study comprehensively analyzes the energy consumption of popular desktop collaborative software, including commercial and free and open source alternatives. By understanding the energy consumption patterns of different collaborative software applications, organizations can make informed choices. The research overview is through task-specific energy analysis. It uncovers insight to empower users and developers to make more energy-conscious choices. Let's talk about research objectives. First one is task-specific energy analysis. It's a methodical examination of energy consumption across various tasks like messaging, file transmission, sending images, and video conferencing sessions of predetermined duration. Second one is energy consumption comparison, a comparative analysis of energy consumption among the most popular collaborative software in the market, both commercial and FOSS. The third one is data-driven insights, empowering end users and developers to make informed decisions regarding their energy consumptions with data-driven insights and which collaborative software applications are the most energy efficient. Various studies have already addressed the energy consumption of data centers and cloud services, highlighting the need for energy efficient solutions. However, the energy consumption or carbon footprint of tasks performed within collaborative software applications remain relatively underexplored, especially when comparing commercial platforms. This study takes a dual perspective, addressing both users and software developers. It empowers users to conserve energy while increasing their awareness of how their actions impact energy consumptions in collaborative software. And simultaneously, it guides developers in creating and maintaining energy efficient applications.
This research searched for a critical question: how do commercial and free and open source collaborative software application behaves when it comes to the energy consumption. By exploring various use scenarios, we aim to uncover which category is more energy efficient. Join us on this journey to understand the impact of your software choices on the environment. Our first hypothesis involved in investigating how enabling and disabling camera during video conference can affect the energy consumption of collaborative software. We aim to understand how the uses of camera impacts the energy uses of both FOSS and commercial applications. For the second hypothesis, our goal is to explore the difference in average energy consumption during text messaging between FOSS and commercial applications. We investigate the energy impact of sending text messages using both FOSS and commercial collaborative application. This hypothesis suggests that there might be difference in energy consumption when sending PDF and zip file of equal size between free and open source software and commercial collaborative software applications. Our experiment will find the results in next section. Also, we investigate the energy consumption implication of sending images in collaborative software application. This hypothesis aimed to understand how transmitting images in JPEG format influences energy consumption in both FOSS and commercial applications. Finally, we want to focus on discerning differences in energy consumption between these two categories, both FOSS and commercial. The aim of this hypothesis is to know how the overall energy consumption differs between commercial and FOSS collaborative software. For all these research questions, we have both null and alternative hypotheses. For all the cases, the null hypothesis is assumed that energy consumption in different usage scenario in FOSS and collaborative software application are same. Alternatively, other hypothesis is energy consumption differs between FOSS and commercial software applications. To test those hypotheses, we selected 4 collaborative software applications as a sample, which are separated under 2 subject families: commercial and free and open source software. The sample subjects are chosen with their popularity in professional work. Additionally, we choose only collaborative software that have native desktop application that works on the experimental environment. For commercial software, Zoom, Skype are chosen due to a survey from Statista in 2020 that showed three-quarters of Americans were using Zoom, Microsoft Teams, or Skype in 2020 for their remote work. Microsoft Teams is not chosen because its native application is not available for the experimental environment. Meanwhile, the open source sample are chosen based on their popularity on GitHub. RocketChat, Mattermost, and Element are respectively awarded 37,000, 26,000, and 10,000 stars in GitHub. RocketChat and Element are chosen as the experiment subject have smooth integration with the experimental environment.
Experiment planning.
The measurement is done using Intel Power Gadget for various tasks in each of the applications. Tasks performed in the collaborative softwares are defined as the factors, which are video conferencing and information sharing. Video conferencing factor has two treatments: mic on, camera off, and mic camera on. While the information sharing factor has four treatments, which are messaging, sending PDF file, sending zip compressed file, and sending image. Its execution duration of factor 1 is set for 2 minutes, with an additional 1 minute of cooling time between each observation. As there are four subjects, this factor has 8 unique experiment combinations. In order to achieve statistical significance, 20 repetitions are run for each of the experiment combination, and therefore there will be total experiment time of 8 hours. Meanwhile, execution duration of factor 2 is set for 1 minute including the cooling time already. As there are four subjects, this factor has 16 unique experiment combinations. In order to achieve statistical significance, 20 repetitions are run for each of the experiment combination, and therefore there will be 5 hours 20 minutes in total of experiment runtime for this factor. Therefore, the total experiment time is 13 hours 20 minutes. The observed data serve as objective evaluation of energy consumption of the collaborative software.
In this section, which is the experiment execution, I'll go through our experiment execution in a straightforward manner, starting with the device we used. The device we used was a Asus ROG Strix Car 2 laptop, which is a gaming laptop with a 1070 NVIDIA GeForce GTX GPU. We conducted our experiments on this laptop, which served as a foundation for our energy assessment in collaborative software applications that we've chosen. For the software and setup, firstly, we have the operating system, which is the Ubuntu 22.04 LTS operating system. We've also installed the latest versions of applications directly from the official sources. To get more information about the versions in the laptop specifications, please refer to the paper. And for verification, we performed dry runs to make sure the applications worked as expected before the experiments. For the network, we used a stable private Wi-Fi network to ensure uninterrupted connection. But we have to note here that we haven't considered network as part of our experiment. As far as automation tools is concerned, we use PyAuto GUI, which is a Python library used for automating various tasks. Python 3.10 scripts were also developed to replicate tasks for consistent experiment runs. Regarding the resource isolation, we to maintain experiment integrity, we tracked the process ID, which is the PID of each usage scenario, enabling precise resource consumption analysis, which will be shown shortly after this slide. We've also wrote custom code for power joule profiling, we used PowerJeweler as our main profiler tool um, to measure the energy consumption during this experiment. We custom coded PyAuto GUI to simulate these scenarios, accurately replicating our usage interaction and monitoring energy consumption using PowerJeweler. In this part, we're going to go through the script that we wrote for our experiment, and we're going to briefly explain the method that we used and the logic behind it. We're not going to go through all of the scenarios because the measuring is pretty much the same. For the video conferencing, we're going to show one from commercial, which is Zoom, in another from open source software, which is RocketChat. For the file sending usage scenario, we're going to demonstrate Skype, showing how we could do the file sending scenario. In our case, it's going to be a PDF sending scenario. In this first method, we get the Zoom PID with the highest resource usage. This method is used to get the highest consuming process ID after the process is initiated, which is in our case a video call. So this method will give us the highest consuming process ID of the app because we specify the name of the app. And here we get access of the highest consuming process ID. Next, we go to the PowerJeweler measurement. As you can see, the PowerJeweler command is used inside the Python script. For the video conferencing, we set a timeout of 10 seconds in this scenario or in this video. This measures the power consumption every 10 seconds for the total number of experiments. In our case, it's just 2 iterations, just for a demonstrative purpose. But in actual reality, it's going to be 5 minutes for each video call repeated 20 times, and it's going to be a timeout of 300 seconds, not just 10. So then, by the end of iteration, in the actual experiment, which is going to be 19, but in our case, it's just one, since we only have 2 iterations, it will stop the measurement and also stop the app completely and exit from the app. Here we get the Zoom meeting ID and passcode through the command line argument. So you can see that's how we get access of the meeting ID and passcode. So once the experiment is started, you can see in the screen that the highest consuming process ID of Zoom is 33008, which you can confirm in the screen. So the highest consuming one is the 33008. You can see it here. So you can see only twice instance of 33008 in the terminal because we run this 2 times. So we can confirm that 33008 is the highest consuming Zoom ID. So PowerJeweler is measuring the energy consumption of that particular process. So same goes for the RocketChat. Same logic applies for the RocketChat. The only difference is that since RocketChat opens Firefox for the video call, then we only monitor the video call. So we filter out highest process with the processing ID of Firefox, not RocketChat, since we're only going to monitor the video conference, and this video conference is going to happen in Firefox. Same logic applies, but the only difference is Firefox, and at the end we close the Firefox and also RocketChat, not just RocketChat. We have to close Firefox again before RocketChat. So in the case of file sending, which is Skype, we also use the same logic to get the highest consuming process ID, but the difference is here we utilize threads and also Python auto GUI for automating the clicks. As you can see, we have 4 methods: one for the message, image, PDF, and zip. So the logic is also the same here. The only difference is the clicks are going to be different since the files are going to be located in a different position. So it's slight modification in the file name, in the file position, sorry, but other thing is the same. We go to the chat option, select the contact, select the touch file, and then choose the file according to the usage scenario. So another thing that we used is a threading or multi-threading in Python. We used threading because since Python AutoGo is introduced in this part, then we have to both start clicking on the system and also run this energy consumption measurement profiling tool. So because of this situation, we have to use trading. Otherwise, it won't work for us quite well. We actually tried it, and we actually struggled a little bit, but we somehow fixed the issue with the trading, and now we have fixed everything, and we got data from this experiment. So in this video, you can see again we only run it twice. So, but an actual experiment is going to be run 20 times. So 20 times is going to be sending a file. So it's important to note that we initially attempted to use an experiment runner. However, we encountered issues with while configuring it. So we had to write our own script. We also faced some challenges with the training, like I said earlier, but we managed to resolve them. Our initial plan was to run each scenario randomly, but it got complicated once we introduced these traits. So instead, what we did was we created a Python script in Ubuntu, and we called the Python scripts one after the other, of course, by separating them using timers. And then we added a timer, yeah, and we ran the whole thing for the experiment. So that's how the actual experiment happened. But for demonstrative purposes, I'm only going to show you only going to show only the few scenarios and how it actually works. Thank you.
Data analysis.
Upon the successful completion of our experiment and data collection, we proceeded to the data analytics. First, where we try to analyze the energy consumption between the commercial and open source collaborative software application that we measured. For open source collaborative software application in the context of Element and Rocket.chat, and in the context of commercial software application, the Skype and the Zoom. So we started by exploring the data that we collected. So using the density plot, QQ plot, and bar chart, which shows some distribution that was not normally distributed, to confirm what we saw from the exploration of the data using when we use the plots, the QQ plot, the density plot, and the histogram. So we proceeded to by applying the Shapiro-Wilks test, which confirmed that the data we got was not normally distributed. When we Shapiro-Wilks test, a p-value of greater than 0.05 helped us in rejecting the null hypothesis that the data was not normally distributed. So assuming we got anything less than 0.05, we would have accepted the fact that the data was normally distributed. But in this case, what we saw was that we had p-values that were greater than 0.05, so it confirms what we saw earlier from the plots, that the data was not normally distributed. So after that, we move on to performing summary statistics to look at what the variances of our data looks like. So the summary statistics shows that the variance of our data was not equal. So since we could confirm that her data was not normally distributed from the Shapiro-Wilks test, we proceeded to test for the energy consumption and doing a statistical analysis by applying the Kruskal-Wilks test. Kruskal-Wilks test compares the independent groups to determine if their population means are equal. And it makes the assumption that one, you must have non-homogeneity of variance, which we saw from our data summary statistics that our variances was not equal. Then the next assumption made by Kruskal-Wilks test was that your scale of measurement must be ordinal. So we add an ordinal scale, and it also makes another assumption that the distribution groups should be similar, which is satisfied by the kind of data that we collected, and also make the assumption of having an independent observation, which was all that we got. So in Kruskal-Wilks test, a p-value of less than 0.05 shows that their statistic significance in difference in their statistical differences in the usage scenarios that we measured. So for all the usage scenarios that we measured, we got a p-value that was less than 0.05, which helped us in rejecting the null hypothesis that we had. So except for the usage scenario where we had to measure the zip versus the PDF sending in commercial software application, where we had a p-value of greater than 0.05, which was 0.250347, and in this case we failed to reject the null hypothesis. Then to confirm or to further confirm that the statistical significance that we saw using the Krokal-Wallis test was not by chance, we proceeded further into doing the effect size estimation analysis, also applying the Krokal-Wallis test. So in this case, it's if an effect size is less than 0.05, which is deemed to be small, it proves that this significant difference is possible that it occurs by chance. Then for effect size that was greater than 0.14, it shows that there's a high significant difference in the measured groups and that this difference was not by chance. So while we measured, we discovered that when we had a p-value, an effect size of 0.14 that was greater than 0.14 for whole usage scenario, which shows that the statistical significance we saw earlier when we did the test was not by chance, except for one, which is also for the PDF and zip comparison in commercial software application, which shows an effect size of less than 0.05. Which also confirmed what we saw earlier from the Krokal-Wallis test analysis. So for this, we completed the phase of our data analytics. It shows that whole our data was significantly different, and we rejected the null hypothesis for most except one. And let's move on into discussing and answering most of our research questions.
Result discussion. Video conference. Our findings suggest that video conferencing is the most energy-intensive activity among the tasks that we analyze. Messaging. We found that text messaging has a relatively low energy impact, making it a more energy efficient alternative to video conferencing. In fact, messaging is the one of tasks that consume the less between the tasks that we observe. Files transmission. In both free and open source software and commercial, we found that sending images consume nearly the same amount of energy as sending a zip or PDF file. However, to be noted that 5 megabytes of zip or PDF might contain much more information to be consumed by users than can be contained in 5 megabyte image. Commercial versus free and open source software. Free and open source collaborative software applications are observed to have a higher energy consumption compared to their commercial counterparts. Carbon emissions.
To acquire the number of carbon emission produced by collaborative software, we utilize the software carbon intensity (SCI) equation by converting the energy consumption in joules to kilowatt hours. And then this energy consumption is multiplied again by the carbon intensity of the place where the observation done, which is the experiment is Netherlands. So we found several findings from our observation from the experiment. The first one is tested commercial applications exhibit a lower carbon footprint compared to free and open source software. The second one is video conference produce the most carbon emission, especially when the camera is turned on. And the third one is messaging produce the less emission.
In conclusion, we want to say that our research highlights the need to consider energy consumption when choosing collaborative software. For our experiment, it becomes evident that commercial application generally exhibits greater efficiency than free and open source applications. As collaborative software become increasingly integral to our lives, our findings empower users and developers to make informed choices for a sustainable digital future. Due to time constraint, we only use 4 apps. In future, researchers can extend this experiment with more application to find more insights.
Thank you for your attention and active participation. I look forward to any questions or discussion you may have.